Good evening. In today's class, we will learn another fundamental theorem named the Green's theorem, and it's the second major theorem after the fundamental theorem of line integrals, and there will be two more toward the end of the course. We're gonna spend some time right at the end of the course to put everything together when it comes to these theorems, because you will see that they have some sort of commonality, starting all the way back from calculus 1 with the fundamental theorem of calculus and moving on through these fundamental theorems we learned here toward the end. And I'm going to use as much as possible some physical intuition as well, which is always useful. Obviously, those of you who take physics courses, those of you who are engineering majors, will go into the physical meaning of some of these tools even deeper. My take is to always pick as much as possible the easiest analogy to illustrate the physical, shall I say, the physical interpretation of the theorem. So the Green's theorem, which we're going to formulate today, I'm not going to prove it, so we're going to state it without proof and then just focus primarily on why it is useful, what it states, and again, like I said, its interpretation. So what are the main ingredients? So first of all, this is for two-dimensional vector fields. So let's make this remark from the onset. There is another version of it called the Stokes theorem, which is basically the 3D generalization of this, which we'll talk about, like I said, toward the end of the course. And the main ingredient will be a vector field with the components P of xy, Q of xy. As we know, these are the typical notations for the components of the vector field. And let's consider also a closed curve. A closed curve such that its interior, is simply connected. I described incorrectly in the previous lesson the definition. I made a correction in the comment on the previous lesson. Simply connected simply means no holes. Again, the most intuitive description of such domain. So if you have a closed loop inside the domain, you can continuously deform that loop to a point, or in other words, the interior of that curve is going to be so in other words, yeah, there is no hole in the interior of that curve. So you can reduce any curve to a point by continuously transforming that closed curve. So that means for the Green's theorem, which we're going to state in a minute, you have this shape. Okay, so let's say this is the curve C, and then let's call D the interior of this curve, the 2D region in this curve. And one convention here, let's say the curve is oriented counterclockwise, which is the so-called positive orientation for a rotation in the two-dimensional space. These are simply conventions. In the beginning, they may seem kind of arbitrary or annoying, but these are just basically conventions so that you are clear on the sign of the integrals that come up in these theorems. It's really nothing special about the convention. It's just basically something that will give us some consistency so that we don't have to always specify, oh, if you do it, if you go over the curve in the opposite direction, then it's going to be this way, or to the opposite sign. So you have basically the formulation of the theorem using one default orientation, which in this case, like I said, is the counterclockwise orientation. And knowing that if you decide to traverse the curve clockwise, you're going to have to add a negative number. So remember, the line integral is going to be the negative of the same line integral if you go over the curve traversed in the opposite direction. So if C is traversed one way, clockwise, counterclockwise, or from point A to point B, minus C, the notation means the same curve traversed in the opposite way. because in some problems, obviously, you will have to, they will ask you, for example, to set up the integral or to compute the integral for a curve traversed clockwise, not counterclockwise. So you can still apply this theorem, but you just have to make sure you change the sign for what you get from the theorem. We'll get to that in a moment, just to make it clear. So what does the theorem state? The theorem states that the line integral for this vector field over this curve, so the line integral over C f dot dr, which again, remember the alternative notation. Traditionally, when we state the Green's theorem, we prefer to use this alternative notation, which I mentioned last time, namely that the line integral can be also stated as the integral of p of xy dx plus q of xy dy. Again, this is simply an alternative notation for the integral of a vector field with two components. The Green's theorem states that this is equal to the double integral over this domain, which is the interior of the curve, of the function given by the difference between partial q with respect to x minus partial p with respect to y dA. So Green's theorem basically relates the line integral over a closed curve to a double integral over the interior of that curve. Okay, so that only in this configuration, right? So for a simply connected curve. So before we get to an example or two, and I'm gonna use an example first, and I'll do it both ways. So I'm gonna actually compute the integral as a line integral, and then I'm gonna compute the integral as a as a double integral, so using the right-hand side of the Green's theorem, and then you decide which one gives you an advantage, so to speak. So perhaps it's probably, let me think a little bit. So let's actually, let's just give a physical intuition of the phenomenon here. I mean, what could be the physical interpretation of the Green's theorem? And that connects also to some of the earlier topics on conservative fields, right? So let's imagine that the vector field in question, actually it's a velocity field in fluid dynamics. So a velocity field in a fluid. Basically each vector gives you the speed of the fluid going to that point in a certain direction. Remember that if you look at the line integral around the curve, that line integral essentially measures the circulation around the curve. Okay, so the left-hand side basically it's the circulation of that fluid along the curve, or how much water actually swirls around the curve. If you imagine the curve is basically, let's say, the edge of an object. So you basically want to measure how much of the fluid goes around that curve. So, I mean, the physical interpretation is kind of maybe a little bit hard to imagine, granted, compared to other theorems we're going to have in this unit. But let's say you actually view the circulation around the big curve as some sort of a macro circulation. Right, over the entire big curve, which you can break down, let's say, into so-called microcirculation. So let's say this entire shape of the fluid is actually divided in tiny, tiny little vortices. So in other words, the big vortex, right, I'm going to make kind of a mess here. The big vortex that goes around the curve C is split into tiny vortices basically around each point. So you imagine basically in the limit, so to speak, because all I'm saying here basically is just a naive description eventually of a Riemann sum. So this Riemann sum essentially is made of by computing these vortices near each point, you take a limit of the Riemann sum, and then you come up with a double integral. So we know the drill already by this point. But what the idea is that what we integrate eventually on the right-hand side are these so-called microcirculations. So if I look at these two nearby macrocirculations inside the big vortex, so I'm going to exaggerate, of course, the dimensions, okay, I mean the size of these microcirculations. Again, we're looking at the counterclockwise circulation. Notice that for any two adjacent microcirculations inside this curve, their effect kind of cancels each other. I mean, if you look at the point of tangent, the microcirculations to the left basically makes a move toward upward, you know, at the point of contact, and the one on the right makes a counter move downward, right, when these two microcirculations come into contact. So roughly speaking, intuitively speaking, all these microcirculations will cancel when you add them up, basically, with the exceptions of the ones that hit the edge of the curve, right? So I mean, at the point of tangents of the microcirculations of the curve, there is no nearby microcirculation to cancel that point of contact. Hence, you're going to have a piece of the total microcirculation coming from that tiny little dot. So in other words, what this theorem states is that if we add up in the limit all these microcirculations in the interior of the domain, which is to say we take the double integral of all those microcirculations, we're going to come up with the total circulation, or the macroscopic or macrocirculation around the boundary of the domain, around the curve C. Okay, so that'll be a physical, intuitive understanding of the theorem. Why would you care about it? Because it gives you the same answer, right? So why would you prefer, you know, to do it via a line integral as opposed to a double integral? Well, the devil is in the details, of course. I mean, the situation can be much easier on one side of the equality as the other. So it can be much easier to compute this integral at a double integral as opposed to a line integral, depending on the case. I would say in particular, if you have the shape of the curve more complicated, especially, for example, if it's made of multiple pieces, you may prefer to use the Green's theorem instead. So here's an example to illustrate what I just mentioned. So let's say the curve in question is actually made of three pieces, three segments, that curve C. So let's say one piece is connecting the point 0, 0 to the point 1, 0, like that, and then continue from 1.10 to the point 1, 2, and back again from point 1, 2 to 0, 0. So that's a closed curve, except that it's made of three pieces. So if you are to, and let's say I want to compute the, and let's call this curve C, right? So I want to compute the line integral. So this curve C actually is made of three pieces, C1, C2, C3, right? So together, these three form the curve C, which is a closed curve. So let's say I want to compute the line integral. By the way, sometimes this line integral is actually denoted like this by a closed loop, you know, to indicate that it's actually, the theorem is only for a closed curve. And the vector field I want to integrate, let's say it's x times y dx. So that's the first component of the vector field, plus x squared y third dy. Okay, so this is P and this is Q. So let's actually do this, like I said, as a line integral first. In the vector notation, remember, this can be written as the dot product between xy, x squared y third, and then dx dy. And then we're going to plug in, of course, the curve, and so on and so forth. But you see, because, well, you know, f.dr, right? Because the curve is made of 3 pieces, I actually have to break the line integral into 3 pieces. The integral over the first piece, c1, f.dr, plus the integral over the second piece, plus the integral over the third piece. None of them is terribly difficult to do, but notice already it's kind of a complication here because, in fact, I have to compute 3 line integrals. And how do I compute 3 line integrals? Well, I'm going to have to come up with a parameterization for each of these 3 pieces, right? So I have to take separately the curve C1. That's the line segment from 0, 0 to 1, 0. So one parameterization. I'm going to go a little bit faster on this, but how do you find the parameterization? Well, you need to find the equation of the line. The equation of the line in this case is basically y equals 0. So if y is equal to 0, you can choose x to be the parameter t. And then, of course, the parameter domain for this will be from 0 to 1. And the second curve, its equation is actually, it's a vertical line, so that's going to be x equals 1. So you could choose y to be the parameter, t. And obviously, if you look at the range for y, then t in this case is also, it's actually from 0 to 2, right? Because it goes from 1, 0 to the point 1, 2. And finally, the curve C3, its Cartesian equation, actually, it's y equals 2x. That's the Cartesian equation of the third curve. So I can choose, again, x to be the parameter. So let's say x is t, and then therefore y is 2t, and the parameter domain in this case is also, it's again 0 and 1, right? Because, yeah, 0 and 1. I should say, to be actually more precise, let's actually be careful here. T is, well, t is from 0 to 1, but we're going to take it from 1 to 0 because we need to make sure we have a closed curve in the end. So we're going to integrate from 1 to 0, that curve. Otherwise, I have to put a minus sign. And then now let's set up the 3 line integrals. Okay, so the first one, let's see if I can fit it in here. The first one is going to be the integral from 0 to 1. We're going to plug in the curve into the vector field, which is xy, x squared, y third. Now, because x is 0, actually when I plug in the, not x is 0, is it? Because y is 0, when I plug in 0 for y, actually it's going to be 0, 0 dot x prime of t, y prime of t. That's just 1, 0. So that's going to be just the integral of 0 dt between 0 and 1. Nothing spectacular. The next one is from 0 to 2. And what do we get in the vector field? We'll have x times y. X times y is 1 times t, comma x squared, which is 1 squared t third. T and t third. Dot r prime, so the derivative of the second curve will be 0 and 1 dt, and then plus the integral from 1 to 0, again from 1 to 0 because we want to keep on going over the curve counterclockwise, so we have to start from the point 1, 2. And now we're going to plug in the last curve t and 2t for x and y, so x times y will be 2t squared. And then, what is it? X squared, y third. X squared is going to be t squared. Y third is going to be 8t third. So altogether 8t to the fifth. And dot product r prime, or the derivative of the curve, which is 1 and 2 dt. So, like I said, the first one is the integral from 0 dt. That's just 0. So the first one doesn't matter. The second integral is of 0 plus t third, so we do the dot product now. So the second integral is of t third dt plus the integral from 1 to 0 of 2t squared times 1 plus 8t fifth times 2, which is 16t to the power 5 dt. Let's finish up the integral. 1 over 4t to the 4 and 0, 2 plus 2t thirds over 3 between 1 and 0. So plug in 0 first and then 1 plus 16 over 6 t to the 6 between 1 and 0. Okay, so let's see what we get. We have 16 over 4, which is 4. Then it's going to be minus 2 thirds, 0 minus 2 thirds, and then 0 minus 16 over 6. Common denominator is 6. We can multiply the first one by 6, so it's 24 minus 4 minus 16 over 6. That's 4 over 6, which is 2 over 3. Okay, so I hope at this point everybody agrees, or most of you would agree, that although none of this is difficult, it is rather tedious. Because once again, to compute a line integral, you have to go through several stages, stages of grief, right? So, you know, take the, find the equation of the curve, find the equation in the parametric form as a vector function, then set it up. And if you have the curve made of multiple pieces, you got to do this for each piece. What would we do, for example, if it was 4 edges, let's say, instead of a triangle? So these are the situations in which the Green's theorem may shine, essentially. So let's see how the whole process would work if we do it via the right-hand side of the theorem, so via a double integral. So stay tuned for the continuation on the next page. Okay, so we put the theorem here on the top here to have it in front of us, and let's see how this plays out if I do it via the Green's theorem. So one more time, actually, let's sketch the domain one more time quickly. It was like that, right? Connecting the points 0, 0, 1, 0, and then 1, 2. And the domain is the interior of the triangle. Okay, so that line integral, which was of xy dx plus x squared y third dy, okay, we don't do it, so we did it via the line integral, or alternatively via Green's theorem, this is going to be the double integral over the domain. Once again, this is p and this is q. The double integral of dq dx is going to be 2x y third, so the partial derivative of q with respect to x, minus the minus the derivative of p with respect to y, which is just x, right? So x times 1 dA. So that becomes a double integral, and let's do it, let's see how it goes as a double integral. We can treat it as a type 1 domain, meaning that, let's look at the typical vertical cut in the domain. That's going to be the integral from 0 to 1 with respect to x on the outside, and the inner bounds for y run from 0. Remember, the equation of the top of the line, top line here is y equals 2x, so it's going to be from 0 to 2x of the function to integrate 2x y third minus x, and then dy. Okay, so the first integral is with respect to y. So what do we get? We get 2x y fourth over 4 minus x times y, with y evaluated between 0 and 2x. And then let's plug in 2x. So we have 2x over 4 times 2x to the power 4 minus x times 2x, and then we plug in 0, so that's just 0. Simplify further, what do we get here? We have 16 times 2, 32 over 8. That's 8. 8x to the fifth altogether minus 2x squared dx. And then finally the last integral, 8x sixth over 6 minus 2x third over 3. And then finally that makes it 8 over 6 minus 2 over 3, 8 minus 2 times 2, which is 4 over 6, 4 over 6, which is, as expected, 2 over 3. So you might not see a big difference. So this is an example in which I still think the double integral is probably easier to go through. It was still a computation to do, but remember, you didn't have to, see, previously you had to have the setup for 3 different curves, have to make sure you take carefully the domain for each of the curves, parameterization, and so on and so forth. So I would say that even in this case, the double integral version of the Green theorem will be easier. Now, there are more dramatic examples in which the advantage of the Green's theorem is even much more pronounced. In other words, you can actually have a situation in which only one side of the equality is doable and the other one is quite impossible. So I like to have fun with examples like this with my students. I put this often in the exams. I'm actually curious if if my students actually watch this and how many of them actually remember this remark I just made. So examples in which I say I have fun with them because the way it's given as a line integral, it's scary. It's actually impossible. So for instance, let's look at the following example. Let's say my closed curve is made of these two parabolas. Y equals x squared and x equals y squared. So the closed curve is the one connecting these two curves, starting again from 0, 0 to the intersection point of the two parabolas, which is 1, 1. For example, going over the y equals x squared and then coming back over the other parabola. So that again can constitute a closed curve with a simply connected domain inside. So let's call this C, right? This curve. And suppose I want the line integral over this closed curve of the following vector field: y plus e to the square root of x dx plus, let's say the second component is 2x plus something crazy, I don't know, cosine of y squared dy. And I put this problem in the test and I say, okay, do it, and be aware that if you use the right tool, then it's going to be easy. Because as a line integral, I didn't even try it. Probably it's impossible, because these terms cannot be integrated, like cosine of y squared and e to the root x. But if you paid attention to the whole discussion up until this point, and you realize that the Green's theorem is applicable, and you actually even mentally set up the Green's theorem, you will realize that these ugly components, e to the square root of x and cosine of y squared, actually don't matter, because they will disappear once you take the partial derivatives in the right-hand side of the Green's theorem. So instead of computing the line integral directly, I'll say, okay, this is via Green's theorem, the double integral over the domain, the interior domain of this curve, dq dx. dq dx actually is just 2 times 1, because cosine of y squared goes away completely. So it's 2 times 1 plus 0, right? That's dq dx, minus dp dy, which is 1 plus 0, because again, e to the root x doesn't depend on y, so it disappears completely when you take partial y of that. So actually, it's just the double integral of a constant, which is as easy as it gets. 2 times 1 minus 1, which is 1 dA. We still have to establish the bounds of the double integral, right? As a type 1 integral, bounds for x are 0 to 1. And then the bounds for y, let's be careful here, the lower bound for y is x squared. And the upper bound for y, you have to solve it from that parabola, is square root of x. 1 dx, dy dx. So the innermost integral is the integral of 1 dy, which is y, evaluated between x squared and root x. And then finally, that means root x minus x squared dx. So 2 more power rules x to the 1/2 integrated makes it 2/3, x to the 3/2 minus 1/3, x to the 3 between 0 and 1. We end up with 1/3. So that's another example, and let me conclude with a couple of remarks before we call it a day and with this this lesson. So, and this is actually quite important. Maybe I should have stated this from the beginning, but it's not a problem. We can deal with it right now. Let's make a connection one more time with conservative vector fields. What does it mean for a vector field with the components P and Q to be conservative? If conservative, that means it has potential. That means it can be given as a gradient of a scalar function. When it is conservative, it happens when dq dx is equal to dp dy, or dp dy equals dq dx. Or in other words, it happens when dq dx minus dp dy is not equal to 0 at all points, at least. So remember what we discussed last time. If the vector field is conservative, okay, so if, let me make it clear here. So it's conservative if dq dx equals dp dy. If they're not, that means not conservative. So let me remind you that if you take a line integral over a conservative field, a line integral over a closed curve for a conservative field, the answer is always 0. Right? Because the integral doesn't depend on the path, and by the fundamental theorem of line integrals, the line integral is going to be the potential of big F evaluated at the initial point and the end point. But the initial point and the end point is the same. Pick any point on the curve. Pick any point on the curve. That can be both initial and terminal point. So if the field is conservative, the Green's theorem, it's not meaningless. It doesn't give you anything useful. Okay, if the field, if F is conservative, Green's theorem basically says 0 equals 0. Okay, because we know already the answer is 0. On the left, we know it's 0 because conservative field on a closed curve, the line integral will be always 0 because of the fundamental theorem of line integrals. The right hand side is 0 because that difference is 0. That is the characterization of the conservative fields, right? That dq dx minus dp dy is equal to 0. So of course the right hand side is 0. So Green's theorem only has values if the field is not conservative. So with that, let's call it a day, and we'll continue next time.